Introduction. Today, we're embarking on a journey into the fascinating world of metallurgy, the art and science of extracting metals from ores and shaping them into the wonders that surround us. Get ready to explore the mechanisms, types, and the vital role metallurgy plays in shaping our modern world. Metallurgy mechanisms. At the heart of metallurgy lies the art of extracting metals from their naturally occurring compounds, known as ores. Through a series of carefully orchestrated processes like crushing, grinding, and smelting, ores surrender their valuable metallic treasures. It's like turning rough gems into polished jewels. The key steps involved in metallurgy. 1. Mining and crushing. Ores are extracted from the Earth's crust through mining. Miners use various methods such as open-pit mining, underground mining, or dredging to access the ores. The extracted ores are then crushed into smaller pieces to increase their surface area, facilitating further processing. Example: iron ore mining. Iron ore is extracted from open-pit mines or underground mines. The extracted ore is then crushed into smaller fragments using crushers or grinding mills to increase the surface area for subsequent processing. 2. Concentration of ores. Many ores are not rich in the desired metal. To increase the metal content, ores undergo a concentration process. Techniques like gravity separation, froth flotation, and magnetic separation are employed to separate the valuable metal-bearing minerals from the waste material. Example: copper ore concentration. Copper ore contains a mix of copper minerals and other impurities. In a copper concentrator plant, the ore is treated to separate the copper-bearing minerals from the gangue, waste, minerals using techniques like froth flotation. 3. Smelting. Smelting involves heating the concentrated ore to a high temperature in a furnace. This process aims to separate the metal from the ore's other components. The metal melts and can be collected, while impurities form a slag that floats on top and can be removed. Example: gold smelting. Gold ore, typically in the form of gold-bearing rocks, is smelted in a furnace at high temperatures. The gold melts and separates from the surrounding rock, while impurities form a slag that floats on top and is removed. 4. Roasting or calcination. Some ores contain sulfide minerals, and roasting or calcination is used to convert these sulfides into oxides. The process involves heating the ore in the presence of air or oxygen. This step is crucial to prepare the ore for further processing. Example: zinc roasting. Zinc sulfide ore is roasted in the presence of air to convert zinc sulfide into zinc oxide. The roasting process removes sulfur and transforms the ore into a more suitable form for further processing. 5. Reduction. Reduction is the process of removing oxygen from metal oxides to obtain the pure metal. This is typically achieved through various methods, such as using carbon, as in the case of iron, hydrogen, or other reducing agents. Example: iron reduction. Iron ore, hematite, is reduced using carbon, usually in the form of coke, in a blast furnace. Carbon reacts with oxygen in the ore to remove the oxygen and release pure iron. 6. Refining and purification. After reduction, the obtained metal might still contain impurities. Refining processes, like electrolysis, distillation, and fractional crystallization, are used to remove these impurities and achieve a higher level of purity in the metal. Example: electrolytic refining of copper. Impure copper obtained from smelting is subjected to electrolysis. Electrolytic cells remove impurities, allowing pure copper to be deposited on the cathode. 7. Alloying. Many metals are rarely used in their pure form. Alloying involves mixing the base metal with other elements to create alloys with improved properties. Alloys often possess enhanced strength, hardness, corrosion resistance, and other desired characteristics. Example: stainless steel. Stainless steel is an alloy of iron, chromium, and nickel. The addition of chromium and nickel enhances corrosion resistance and durability, making it suitable for applications like kitchen utensils and medical instruments. 8. Shaping and forming. Once the desired metal or alloy is obtained, it can be shaped and formed into various products. Processes like casting, forging, rolling, extrusion, and machining are employed to transform the raw material into usable forms such as sheets, bars, wires, and intricate components. Example: aluminum extrusion. Aluminum billets are heated and forced through a die to create various shapes, such as tubes or frames. Extrusion allows for the production of intricate and customized aluminum profiles. 9. Heat treatment. Heat treatment processes are applied to metals to alter their mechanical and physical properties. Processes like annealing, quenching, tempering, and case hardening can enhance hardness, strength, toughness, and other characteristics. Example, steel tempering. After quenching to achieve high hardness, steel is tempered by reheating it to a controlled temperature. This process reduces brittleness and improves toughness without sacrificing too much hardness. 10. Finishing and coating. Finally, the metal products are often subjected to surface treatments like polishing, plating, and coating to improve their appearance, durability, and resistance to corrosion. Example, chrome plating. Chrome plating is applied to automotive parts, faucets, and other objects. A layer of chromium is electroplated onto the surface to enhance its appearance and provide corrosion resistance. These steps collectively transform raw ores into valuable metals and materials that serve as the foundation for a wide range of industries and applications. Each step requires precision, expertise, and a deep understanding of the metallurgical properties of the materials involved. Types of metallurgy. Metallurgy wears different hats, each tailored to the nature of the metal. Pyrometallurgy involves intense heat to extract metals, while hydrometallurgy employs liquids to dissolve and recover them. Electrometallurgy harnesses electricity to separate metals. These techniques are like crafting different recipes to cook up the desired metal. Importance of metallurgy. Imagine a world without metallurgy, no gleaming skyscrapers, no airplanes soaring through the skies, and no shiny gadgets we rely on daily. Metallurgy enables us to harness the strength, durability, and malleability of metals, transforming them into tools, structures, and technologies that shape our modern lives. Applications of metallurgy. Think of metallurgy as the silent hero behind the scenes. From sturdy steel used in construction to lightweight aluminum in transport, and precious metals in electronics, metallurgy is the backbone of industries. Even medical devices and renewable energy technologies rely on the magic of metallurgy. Conclusion. As we wrap up our journey through the world of metallurgy, remember that this field is the alchemy that turns raw materials into life-changing innovations. From extracting metals to crafting revolutionary materials, metallurgy keeps our civilization moving forward. So, whether you are gazing at a towering skyscraper or holding a sleek smartphone, remember that it all began with the art of metallurgy.